Weighted and Directed Networks, a graduate lecture companion. The aim is to deepen and connect the ideas from lecture, to make explicit the considerations that distinguish these networks from the simple, undirected, unweighted case, and to survey the metrics and applications that matter most. As with our other companions, there are no written equations. Where an equation is important, it is named and explained in words. Hashtagger Part 1. Why Weight and Direction Change the Game. Most introductions to network science begin, sensibly, with the simple graph, a set of nodes joined by edges that are binary. An edge is either present or absent, and symmetric. If A connects to B, then B connects to A. This simple graph is a wonderful pedagogical object and a great deal of structural insight, degree distributions, clustering, components, small world geometry can be developed on it. But it is, for most real systems, a drastic idealization. Real ties differ in intensity, and many real ties point one way. A simple graph that records merely whether two countries trade erases the fact that the United States and China exchange goods worth thousands of times more than two small neighboring economies, and a simple graph that records merely whether one neuron connects to another erases the fact that the signal flows from the first to the second and not back. Weight restores intensity. Direction restores asymmetry. Together they recover most of the information that binarization and symmetrization threw away. And in doing so, they change nearly every metric, every algorithm, and every interpretation we carry over from the simple case. The thesis of this companion, and of the lecture it accompanies, is that weighted and directed networks are not merely simple networks with decorations. The decorations interact with the structure in ways that force us to rethink even the most basic quantities. Degree splits into several distinct notions, connectivity fragments into strong and weak varieties. Centrality, which on an undirected, unweighted graph is a relatively settled matter, becomes a subtle and contested family of measures whose differences encode genuinely different theories of importance. Clustering must be redefined, and there is no single agreed redefinition. Community detection acquires a directional, flow-based character, and a set of practical considerations: what the weights actually mean, whether they represent affinity or cost, how to compare and normalize them, how to extract a meaningful skeleton from a dense weighted network, becomes unavoidable. We will take these in turn, but the unifying message is that weight and direction repay careful, separate, and combined attention. It helps to fix the two axes clearly at the outset, because they are independent and a network may have either both or neither. A network is weighted when its edges carry a real valued magnitude, a weight or strength, rather than mere presence. A network is directed when its edges are ordered pairs, distinguishing the source from the target, so that an edge from A to B is a different object from an edge from B to A, and either both or neither may exist. The four combinations, unweighted undirected, weighted undirected, unweighted directed, and weighted directed, form a natural progression of richness, and the fully general case, the weighted directed network, is where most empirical network science now lives. A trade network is weighted and directed. A brain connectome is weighted and directed. A citation network is unweighted but directed. A correlation network of stock returns is weighted but undirected. Knowing which quadrant your system occupies is the first analytical decision you make, and it should be a deliberate one rather than a default. Hashtag Part 2, Representation and the Adjacency Matrix. Everything begins with representation, and the natural representation of any of these networks is the adjacency matrix, the square array whose rows and columns are indexed by nodes and whose entries record the edges. In the simple case, this matrix is binary and symmetric. The two generalizations correspond exactly to relaxing those two properties, and it is worth seeing them as matrix properties because so much of the theory follows from linear algebra. Weighting the network means the adjacency matrix is no longer binary. Its non-zero entries hold the edge weights, real numbers that may represent flows, capacities, similarities, distances, frequencies, or probabilities. Directing the network means the adjacency matrix is no longer symmetric. The entry in row Y and column J, recording an edge from I to J, need not equal the entry in row J and column 1. This asymmetry is not a minor technicality. A symmetric real matrix, the kind that describes an undirected weighted network, has a guaranteed set of real eigenvalues and orthogonal eigenvectors, the comfortable terrain of the spectral theorem, and an enormous amount of network theory, spectral clustering, eigenvector centrality, diffusion analysis, leans on that guarantee. An asymmetric matrix, the kind that describes a directed network, may have complex eigenvalues, may not be diagonalizable at all, and forces us to distinguish left eigenvectors from right eigenvectors. Many of the complications we will meet in directed centrality are, at bottom, consequences of losing the spectral theorem. When you find directed network methods behaving strangely, asking whether the underlying matrix is still symmetric is often the fastest route to understanding why. A practical representational point deserves emphasis because it shapes computation. Real networks are sparse. The adjacency matrix is overwhelmingly zeros, and we never store it densely. We store edge lists or adjacency lists, and for directed networks we typically keep both an out adjacency listing each node's successors and an in adjacency listing each node's predecessors, because algorithms need to traverse edges in both senses, forward to follow flow and backward to trace its origin. The fact that we need two such structures, where the undirected case needs one, is the data structure shadow of the conceptual fact that direction doubles the kinds of questions we can ask of every node. A final framing concept from lecture is worth restating. The meaning of a weight is not given by the data, it is asserted by the modeler. The same number can play opposite roles. If an edge weight is a similarity, a flow, or a capacity, then large weights mean strong, close, well-connected ties, and we want paths that accumulate large weights. If an edge weight is a distance, a cost, or a travel time, then large weights mean far apart, and we want paths that accumulate small weights. This affinity versus cost distinction governs whether shortest path algorithms should minimize or whether we should first invert the weights, whether high strength means central or peripheral, and whether a community is a region of high or low internal weight. Almost every error students make with weighted networks traces back to a slippage between these two readings of what a weight is. Decide, explicitly and early, which one your weights are. Hashtag part 3. Degree, strength, and the local structure of weight and direction. Hashtag splitting the degree. On a simple graph, degree, the number of edges incident to a node, is the most basic and most informative local quantity. Weight and direction each split it, and understanding the split is the foundation for everything local. Direction splits degree into in-degree and out-degree, the number of incoming and outgoing edges respectively. This is not a cosmetic distinction. A node may be a sink, receiving many edges and sending few, or a source, sending many and receiving few, and the two roles are often functionally opposite. In a citation network, a high in-degree marks an influential, much-cited paper, while a high out-degree marks merely a paper with a long bibliography. In a food web, direction encodes who eats whom, so in-degree and out-degree separate predators from prey. On the web, in-degree is a rough proxy for authority, while out-degree is not. Consequently, a directed network has two-degree distributions, not one, and they may have entirely different shapes, one heavy-tailed and one not, and they may be correlated or anti-correlated across nodes, a correlation that itself carries meaning. The first thing to do with any directed network is to look at both distributions and their joint structure, never just a single conflated degree. Weighting splits degree in a different direction, giving rise to node strength, defined as the total weight of a node's incident edges, the weighted analog of degree. A node may have few connections, each carrying enormous weight, or many connections, each carrying tiny weight, and degree alone cannot tell these apart, while strength can. Combine weight and direction and we obtain the full local quartet, in-degree and out-degree counting connections by direction, and in-strength and out-strength summing weights by direction. A country may import from few partners, but in vast quantity, giving low in degree but high in strength. A neuron may receive many weak inputs and a few strong ones. The relationship between a node's degree and its strength is itself a studied quantity. Empirically, strength often grows as a power of degree, and whether that exponent is 1, meaning weights are independent of degree, or greater than 1, meaning high-degree nodes, also tend to have disproportionately heavy edges, distinguishes a network where hubs are merely well connected from one where hubs are also intensely connected. Air transportation is the textbook example of the latter, where the busiest airports not only have many routes but carry especially heavy traffic on them. Hashtag looking inside a node's weights. Strength summarizes a node's weights by summing them, but the distribution of weight across a node's edges matters too, and several local measures capture it. The disparity, or its relative sometimes discussed under the heading of participation, asks whether a node's strength is spread evenly across its edges or concentrated on a few. A node whose strength is dominated by one heavy edge behaves very differently, in terms of robustness and flow, from a node whose strength is uniformly distributed, even when their total strength and degree are identical. The disparity measure essentially computes the effective number of edges that actually carry the node's weight, and comparing it to the actual degree reveals concentration. This local heterogeneity of weights is one of the features that simple and even merely weighted summed descriptions miss, and it often turns out to be where the interesting structure lives, identifying nodes that depend critically on a single tie. Reciprocity and local asymmetry. A purely directed phenomenon with no undirected analog is reciprocity, the tendency for an edge from A to B to be accompanied by a reciprocating edge from B to A. Reciprocity is measured globally as the fraction of directed edges that are reciprocated, and it ranges from networks that are almost entirely one-way to networks that are almost entirely mutual. It is a fundamental descriptor of a directed network's character. Email and social following networks have intermediate reciprocity that reveals the balance of mutual versus one-sided relationships. The World Wide Web has relatively low reciprocity, and a well-measured reciprocity must be judged against what chance alone would produce given the network's density, since dense networks reciprocate by accident more often. More refined treatments examine reciprocity at the level of individual node pairs and even reciprocity of weights, asking not merely whether a returns B's edge, but whether it returns it in comparable magnitude, which in a trade or flow network distinguishes balanced exchange from lopsided dependence. Reciprocity is the simplest example of a structural quantity that exists only because direction exists, and it foreshadows the richer directed motifs we meet later. #E Part 4. Paths, Connectivity, and Components. #AVER, Weighted Distance and Shortest Paths. On a simple graph, the distance between two nodes is the number of edges on the shortest connecting path, and breadth-first search finds it. Weighting changes the meaning of shortest. If weights are costs or distances, the shortest path is the one minimizing the summed weight, and the algorithm of choice is Dijkstra's, which generalizes breadth-first search to non-negative edge costs, or its weighted graph relatives for harder cases. If, instead, weights are affinities or flows, summing them along a path is the wrong operation entirely, because a path through many strong ties should be considered short, not long. The standard remedy is to transform affinity weights into distances before computing paths, most commonly by inverting them, so that a strong tie becomes a short step, and only then running a shortest path algorithm. This transformation is a modeling choice with real consequences, and different reasonable transformations yield different geometries. There is no canonical map from strength to distance, and the analyst must justify the one chosen. This is the path-level manifestation of the affinity versus cost distinction, and it is the single most common place where weighted network analyses go quietly wrong. A subtlety worth flagging is that weighted shortest paths often differ from topological shortest paths. The path with the fewest hops may not be the path of least cost, and the path of greatest accumulated strength may wind through many intermediaries. Which notion is appropriate depends on the process the network supports. For a packet that pays a latency at each hop count matters. For a traveler paying per mile, summed distance matters. For an epidemic spreading along strong contacts, an inverse strength distance may matter. Stating which process you are modeling resolves the ambiguity, and refusing to state it leaves every downstream path-based metric, including betweenness and closeness, ill-defined. #Strong and weak connectivity. Direction fractures the notion of connectivity, and this is one of the most important conceptual shifts in moving from undirected to directed networks. In an undirected graph, two nodes are either connected by some path or they are not, and the network decomposes cleanly into connected components. In a directed graph, there are two distinct notions. Two nodes are strongly connected. If there is a directed path from each to the other, respecting edge directions in both senses, they are weakly connected if there is a path between them. When we ignore directions and treat every edge as undirected, these give two different decompositions: the strongly connected components, maximal sets of mutually reachable nodes, and the weakly connected components, maximal sets connected in the underlying undirected graph. Every strongly connected component sits inside a weakly connected one, and the two can differ enormously. The classic illustration is the bow tie structure of the World Wide Web, and it is worth carrying as a mental model for all large directed networks. Such networks typically contain one giant strongly connected component, the central knot of the bow tie, within which one can navigate freely following links in both directions. Around it sit an in-component of nodes that can reach the core but cannot be reached from it, the upstream sources, and an out-component of nodes reachable from the core but with no path back, the downstream sinks. together with tendrils and disconnected pieces. This decomposition has no undirected analog, and it immediately reframes questions of reachability and influence. A node's importance depends not only on how many nodes it connects to, but on which part of the bow tie it occupies. Reachability itself, the set of nodes a given node can reach by directed paths, becomes a per-node quantity rather than a global yes or no, and the distribution of reachable set sizes is a genuine structural fingerprint of a directed network. Whenever you receive a new directed dataset, computing the strongly and weakly connected components and sketching the bow tie is among the most informative first moves available. Part 5, Centrality, where direction and weight matter most. Centrality, the family of measures that rank nodes by structural importance, is where weight and direction have their most consequential and most subtle effects. On a simple undirected graph, the major centralities are relatively well behaved and often correlated. On a weighted directed graph they diverge sharply, and choosing among them amounts to choosing a theory of what importance means. We organize them by the kind of importance they encode. #Worth degree and strength centrality. The simplest centralities are the local quantities we have already met, promoted to importance scores. In a directed network, in-degree centrality and out-degree centrality measure importance as popularity versus gregariousness, receiving versus sending, and their weighted versions, in-strength and out-strength, weight those counts by intensity. These are cheap, interpretable, and often a strong baseline, but they are purely local. They count a node's immediate ties without regard to the importance of the nodes on the other end. The deeper centralities all share one ambition: to make a node's importance depend on the importance of its neighbors, and they differ in how they handle the circularity and the asymmetry that this ambition creates in a directed setting. Eigenvector Centrality and its directed difficulties. Eigenvector centrality formalizes the idea that a node is important if it is connected to important nodes, defining each node's score as proportional to the sum of its neighbors' scores, which makes the score vector an eigenvector of the adjacency matrix, specifically the one associated with the largest eigenvalue. On an undirected, hence symmetric, network, this is well behaved. The Perron-Frobenius theorem guarantees a unique positive leading eigenvector, and the scores are sensible. On a directed network, the construction runs into exactly the troubles foreshadowed earlier. The matrix is asymmetric, so left and right eigenvectors differ, and one must decide whether importance flows from a node to those it points to, or from a node to those that point to it. Worse, directedness creates nodes and regions with no incoming paths from the rest, sources and the in-component of the bow tie, which receive zero. Eigenvector centrality, and can starve their downstream neighbors of score, making naive eigenvector centrality unstable or degenerate on real directed networks. The history of directed centrality is in large part a history of fixes for this pathology, and the two most important fixes, Katz Centrality and PageRank, are worth understanding as responses to it. Katz, PageRank, and hits. Katz Centrality repairs eigenvector centrality by giving every node a small amount of free baseline centrality and then adding the centrality that flows in along directed paths, with longer paths discounted geometrically by an attenuation factor. The free baseline ensures that even nodes with no incoming edges receive a positive score and can pass score downstream, curing the starvation problem, while the attenuation factor must be kept below a threshold set by the network's leading eigenvalue for the sum over paths to converge. Katz centrality thus measures importance as the discounted volume of directed walks that terminate at a node, and it is a natural, tunable importance score for directed networks. PageRank, the algorithm that organized the early web and remains a cornerstone, can be read as a further refinement of the Katz idea with one crucial addition. It normalizes each node's outgoing influence by its out degree, so that a node with many outgoing links passes only a small share of its importance along each one. The interpretation is a random walk. Imagine a walker following directed edges at random, and at each step, with some probability, teleporting to a node chosen uniformly at random rather than following an edge. PageRank is the long-run fraction of time this walker spends at each node, the stationary distribution of that teleporting random walk. The teleportation, governed by the famous damping factor conventionally set near 85%, solves two problems at once. It rescues the walker from dangling nodes that have no outgoing edges, where it would otherwise get stuck, and it guarantees that the walk has a unique, well-defined stationary distribution even on a network that is not strongly connected. PageRank generalizes gracefully to weighted networks by having the walker follow edges with probability proportional to their weights, and to personalized variance by teleporting to a biased set of nodes, which underlies recommendation and the personalized importance scores common in applications. Conceptually, PageRank is the place where directedness, weighting, random walks, and the spectral theory of asymmetric matrices all meet, and it rewards careful study as the exemplar of the whole subject. A complementary idea is the hits algorithm, which recognizes that in a directed network importance has two faces. Hits assigns every node two scores, a hub score and an authority score, defined by a mutually reinforcing relationship. Good authorities are pointed to by good hubs, and good hubs point to good authorities. A node is a strong authority if many strong hubs link to it, and a strong hub if it links to many strong authorities. This decomposition fits directed networks where the roles of source and sink are genuinely distinct, the web being the original example, where authoritative content pages and link-rich directory pages play different roles. And it captures something that any single score centrality necessarily blurs. The hit scores are themselves eigenvectors of matrices built from the adjacency matrix and its transpose, which is the formal reason two scores fall out naturally from a directed structure. #offer betweenness and closeness in the weighted directed setting. The path-based centralities, betweenness and closeness, carry over to weighted directed networks, but inherit all the path definition subtleties of Part 4. Betweenness centrality measures importance as brokerage. A node is central if it lies on many shortest paths between other pairs of nodes, making it a bottleneck through which flow must pass. In the weighted directed setting, shortest path must be defined with the correct weight interpretation and must respect edge directions, so that a node brokers only the directed flows that genuinely route through it, and the resulting betweenness can differ dramatically from its undirected, unweighted counterpart, identifying gatekeepers that control directed flow. Closeness centrality measures importance as proximity, scoring a node by the inverse of its total distance to all others, and in a directed network, it again splits in two, an outward closeness based on distances from the node to others, and an inward closeness based on distances from others to the node, which need not agree. Both measures also require care about reachability, since in a directed network, many pairs may have no connecting path at all, and the standard remedies, restricting to reachable pairs or using harmonic variants that sum inverse distances and thereby tolerate infinite distances gracefully, are themselves modeling choices. The general lesson recurs: every path-based centrality, when ported to weighted directed networks, acquires a direction-aware definition and a weight interpretation dependency that the simple graph version concealed. #U Part 6. Clustering, Motifs and Mesoscale Structure. Generalizing the clustering coefficient. The clustering coefficient, which on a simple graph measures the probability that two neighbors of a node are themselves connected, the tendency of triangles to close, resists any single generalization to weighted and directed networks, and the proliferation of competing definitions is itself instructive. For weighted networks, the question becomes not merely whether a triangle exists, but how strong it is, and several proposals exist. One influential definition weights each closed triangle by the average strength of the two edges a node contributes, so that triangles built from heavy edges count more, capturing whether a node's strong ties are themselves interconnected. Another defines triangle intensity through the geometric mean of all three edge weights, normalized by the maximum weight in the network, which rewards triangles whose three edges are all substantial rather than two strong and one negligible. These definitions can disagree about which nodes are most clustered, and the disagreement is not a defect to be resolved, but a reflection of genuinely different questions. Is it the existence of weighted triangles that matters, or their balanced intensity? Direction multiplies the possibilities further. Around any node, a triangle of three directed edges can be oriented in several distinct patterns: cyclic triangles where the edges chase one another around the loop, and various transitive or middleman configurations where one node feeds two others or sits between a source and a sink. A directed clustering coefficient must specify which of these orientation patterns it counts, and different processes care about different patterns. A feed-forward transitive triangle is the signature of a regulatory cascade, while a cyclic triangle signals feedback. The upshot is that clustering in weighted directed networks is not one number but a small family of numbers, and reporting a single undirected, unweighted clustering coefficient for such a network discards exactly the orientation and intensity information that makes the local structure meaningful. #REG directed motifs. This observation generalizes beyond triangles into the theory of network motifs, small connected subgraphs that recur in a network far more, or far less, often than chance would predict. Judged against a randomized null model that preserves basic features like the degree sequences. In directed networks, motifs become especially powerful because the number of distinct, small directed subgraphs is large. 3 nodes alone admit 13 distinct connected, directed patterns, and the over- or under-representation of particular patterns reveals functional building blocks. The most celebrated example is the feed-forward loop in gene regulatory and neural networks, a 3-node directed motif that appears far more often than chance, and that, when analyzed dynamically, performs useful information processing functions such as filtering transient signals. Motif analysis is fundamentally a directed and often weighted enterprise. The orientation of the edges is the whole point, and stripping direction would erase the very patterns of interest. Motifs sit at the mesoscale, between local node properties and global community structure, and they are one of the clearest demonstrations that direction carries functional, not merely descriptive, information. #where community detection with weight and flow. At the largest mesoscale, community detection, partitioning a network into densely interconnected groups, must also be rethought. The dominant framework on undirected weighted networks is modularity maximization, which scores a partition by how much more internal edge weight the communities contain than would be expected under a degree-preserving random null model, with popular optimizers such as the Louvain and Leiden algorithms operating directly on weights by treating strength where the unweighted version would treat degree. Weighting integrates fairly naturally here, since modularity is defined in terms of edge weights from the start. Direction is harder. A directed generalization of modularity must decide what an expected edge is when out-degree and in-degree differ, and the resulting directed modularity rewards communities that respect the asymmetry of connections, but modularity-based methods on directed networks can miss something important, because what often defines a community in a directed system is not edge density, but flow containment, the tendency of a process moving through the network to remain within a group for a long time before escaping. This insight motivates flow-based community detection, most prominently the map equation and its infomap algorithm, which frames community detection as a compression problem. Describe the trajectory of a random walker on the directed weighted network as efficiently as possible, and the best description uses a code book that groups together nodes the walker tends to stay among. Because the random walker follows directed weighted edges, this approach is intrinsically suited to directed flow systems, and it tends to find communities that genuinely trap flow rather than merely concentrate links. The contrast between modularity, which is a density-based notion of community, and the map equation, which is a flow-based notion, is one of the deepest conceptual choices in the analysis of directed weighted networks, and which is appropriate depends, once again, on whether you care about who is connected to whom or about how something moves through the structure. For systems defined by transport, trade, information, or dynamics, the flow-based view is often the more faithful one. #U Part 7, Null Models, Randomization, and Statistical Care. A recurring theme above is that almost every observed quantity, reciprocity, clustering, motif counts, modularity must be judged against what would be expected by chance, and this raises the question of what chance means for a weighted directed network. The answer is a null model, a randomized ensemble of networks that preserves some properties of the observed network while scrambling others, against which the observed value is compared. For simple graphs, the canonical null model is the configuration model, which preserves the degree sequence while randomizing connections. For directed networks, the configuration model must preserve both the in-degree and the out-degree sequences jointly, and may additionally be asked to preserve reciprocity, which substantially changes what counts as surprising. For weighted networks, randomization must decide whether to preserve the strengths, the degrees both, or the full weight distribution. And these choices are not interchangeable. A motif or a community that looks significant against a weak null model may dissolve against a stronger one that preserves more structure. The discipline of choosing and stating the null model is part of doing weighted directed network analysis honestly, and many published claims about structure are really claims about a comparison to a particular, often unstated, null model. When you read or write such an analysis, ask what was held fixed and what was randomized, because the answer determines what the result means. #U Part 8. Practical considerations that separate weighted directed analysis Beyond the metrics, a set of recurring practical problems distinguishes working with weighted directed networks from working with simple graphs, and a graduate practitioner should anticipate all of them. The first is the meaning and scale of weights. Weights arrive in whatever units the data-generating process supplies: dollars, packets, correlation coefficients, co-occurrence counts, synaptic strengths, and they are frequently heavy-tailed, spanning many orders of magnitude. Whether to analyze raw weights, logged weights, or rank transformed weights is a consequential choice that changes every weighted metric, and there is no universally correct answer. It depends on whether the process of interest responds to absolute magnitudes or to relative ones. Relatedly, weights are often noisy, and a measured weight near zero may represent a genuine weak tie or merely measurement error, which is why thresholding, discarding edges below some weight, is common and dangerous. A poorly chosen threshold can manufacture or destroy structure, and the sensitivity of conclusions to the threshold should always be checked rather than assumed away. The second is the related problem of backbone extraction. Many empirical weighted networks are dense, even nearly complete, with most node pairs sharing some small weight, and the meaningful structure is carried by a sparse subset of significant edges. Naive thresholding by a global weight cutoff fails here because it systematically removes the edges of low-strength nodes while keeping all the edges of high-strength nodes, conflating significance with mere magnitude. The principled remedy is a statistically motivated filter, the best known being the disparity filter, which evaluates each edge against a null model local to each node, asking whether a given edge carries more of its node's strength than would be expected if that node's strength were distributed uniformly across its edges, and retaining edges that are locally significant from the perspective of at least one endpoint. Backbone extraction is a step with no analog in simple graph analysis, and getting it right is often the difference between seeing real structure and seeing an artifact of density. The third is the correlation structure among the local quantities. Because weighted directed networks have several local descriptors per node, in degree, out degree, in strength, out strength, their mutual correlations are themselves objects of study. Degree strength correlation tells us whether hubs are also heavily loaded. Degree correlations across edges, the directed and weighted generalizations of assortativity, tell us whether high out degree nodes tend to point to high in degree nodes. A four-way set of assortativity coefficients replacing the single assortativity of an undirected graph. These correlations encode real organizational principles, such as whether a network is hierarchical, with flow running consistently from one stratum to another, or egalitarian, and they are invisible to any analysis that collapses the local quartet into a single degree. The fourth is computational and statistical scale. Directed networks require maintaining and traversing edges in both orientations. Weighted shortest paths require priority queue algorithms rather than simple breadth-first search. Spectral methods on asymmetric. Matrices require handling complex eigenvalues and the distinction between left and right eigenvectors, and many metrics, betweenness above all, are expensive on large networks and are computed approximately by sampling. These are not exotic concerns but everyday realities of applied work, and they shape which analyses are feasible at the scale of real systems with millions of nodes. #U Part 9. Applications, where the distinctions earn their keep. The abstractions above are motivated by systems in which weight and direction are not optional refinements, but the essence of the phenomenon. A survey of these grounds the theory, and shows why the simple graph idealization is so often inadequate. International trade forms a weighted directed network par excellence. Nodes are countries, directed edges are exports from one to another, and weights are trade volumes spanning many orders of magnitude. Here, in-strength and out-strength separate importers from exporters. The bow tie and reachability structure reveal economic dependency. Weighted, directed community detection uncovers trade blocks. And weighted assortativity exposes the hierarchical core periphery organization of the global economy. None of this survives binarization or symmetrization. Closely related are financial networks, where directed weighted edges represent loans, payments, or exposures between institutions, and where directed centrality and flow analysis bear directly on systemic risk and contagion, the cascading propagation of failure along directed liabilities, a topic of intense interest since the financial crisis. Neuroscience supplies two canonical examples. The connectome, the wiring diagram of a nervous system, is directed, signals flow from presynaptic to postsynaptic neuron, and weighted by synaptic strength, or the number of connections, and its motifs. Directed clustering and rich club organization of strongly interconnected hubs are central to understanding information processing. Functional brain networks, by contrast, are typically weighted but undirected, with edges representing statistical correlation between regional activity, illustrating that the same domain can present different quadrants depending on the measurement. Biology more broadly is replete with weighted directed networks, gene regulatory networks, where directed edges represent one gene's regulation of another, and motifs like the feed-forward loop carry functional meaning. Metabolic networks of directed biochemical reactions, and food webs, where directed edges encode energy flow from prey to predator, and weights encode flux, making trophic level and directed path analysis the natural tools. Information and infrastructure systems are inherently directed and weighted. The web's hyperlink graph, directed, and the birthplace of PageRank and hits, and the bowtie picture, remains the archetype. Citation networks are directed and acyclic in idealization, since a paper can cite only earlier work, which gives them special structure that ordinary directed network methods must respect. Transportation and mobility networks, flights, shipping, commuting, road traffic, carry directed weighted flows where weighted betweenness identifies critical bottlenecks and weighted shortest paths underlie routing. Communication networks, email, messaging, phone calls, are directed and weighted by frequency or volume, and their reciprocity and directed community structure illuminate social organization. Across all of these, the pattern is the same. The questions practitioners actually care about: who controls flow, who depends on whom, how does something spread, where are the bottlenecks, which groups trap dynamics, are precisely the questions that only weight and direction can answer, and a simple graph analysis would either be unable to pose them or would answer them wrongly. #U Part 10, Synthesis. The through line of this companion is a single idea, with many consequences. Weight and direction are not embellishments on the simple graph, but distinct dimensions of structure that interact with every level of analysis. Direction breaks symmetry, and the broken symmetry propagates outward, splitting degree into in and out, splitting connectivity into strong and weak, splitting closeness into inward and outward, demanding two-faced centralities like hubs and authorities, costing us the spectral theorem and with it the easy guarantees of undirected eigenvector methods, and creating entirely new phenomena: reciprocity, the bowtie, directed motifs that have no undirected counterpart. Weight restores intensity, and intensity propagates outward too, replacing degree with strength, demanding that we specify whether a weight is an affinity or a cost before any path can be computed. Introducing local heterogeneity through disparity, complicating clustering into a family of competing definitions, and forcing the practical disciplines of normalization, thresholding, and backbone extraction. Combined, in the fully general weighted directed network, where most empirical work now lives, these dimensions require us to hold several local descriptors per node, to choose path, definitions and null models deliberately, to distinguish density-based from flow-based notions of community, and at every turn to state the interpretation that gives our numbers meaning. The practical counsel that follows is straightforward. Identify your quadrant first, and resist the temptation to binarize or symmetrize for convenience, since that convenience discards the very information that motivated the study. Decide explicitly whether your weights are affinities or costs, because that single decision cascades through paths, centralities, and communities. Report the local quartet rather than a conflated degree. Examine both degree distributions and the strength distribution, and look at their correlations. Choose path-based and community methods according to whether you care about connection or about flow. Judge every structural claim against a clearly stated null model, and check the sensitivity of your conclusions to thresholds and transformations. And let the application discipline you, the trade economist, the neuroscientist, and the web engineer, all reach for weighted directed methods, not out of mathematical taste, but because their systems are genuinely weighted and directed. And the methods exist to recover what those systems actually are. The simple graph is where we learn the concepts. The weighted directed network is where we meet the world.